Welcome to this first series of videos where we're going to look at forces of motion, and in particular we're going to start off with looking at Newton's first law, which will form the basis of everything that we do this week with regards to forces and motions. Okay, so what is Newton's first law? So Newton's first law states that if forces acting on an object balance, the object will remain at rest, in equilibrium, or moving with constant velocity. Okay, so the most important aspect of this is obviously if an object is at rest or at constant velocity, then the forces acting on it will balance out. Now we need to add a few more details to this, that the horizontal forces and the vertical forces balance each other. Okay, so that's quite an important detail. Okay, now in terms of a physics type explanation, we'll call the resultant force equal to zero. So the resultant force is basically the sum of the forces has to equal to zero. Okay, if an object is at rest, i.e. in equilibrium or moving with constant velocity. Okay, so we've got this very simple example here. A book with weight 130 newtons is placed on the table as shown. Find the value of the reaction force of the table on the book. So I'm just going to draw the weight arrow. Yep, 130 newtons. Now the book is at rest on the table. So if it's at rest on the table, there must be a force that balances that weight in the same direction, okay, in the same line of action as the weight. Okay, and that is our normal reaction force. Now, because it's in equilibrium, that these two forces must balance each other. Therefore, the reaction force is also 130 newtons. Okay, so that's invoking Newton's first law. Okay, that the resultant forces vertically are equal to zero. Okay, they balance each other out. It's a really simple example. Now let's look at example 2. Four forces are acting on an object as shown. The object moves at a constant speed of 5 meters per second. Find the forces X and Y. Now we've got to be quite careful here. Okay, if it's moving at a constant speed or velocity of 5 meters per second, okay, then it's not accelerating. If it's not accelerating, then what we can assume is that there is no resultant force. Okay, there is no overall force which is causing it to speed up or the velocity to change. Okay, so the velocity is remaining the same. Therefore, again, I look at my forces horizontally and vertically. Okay, so what I'm going to look at my forces horizontally. I'm going to take the right direction to be positive. Now what I can clearly see is that any forces to the right I'm going to take as positive, any forces to the left I'm going to take as negative. Therefore X, which is this force here, minus 5, horizontally, that resultant force must be equal to 0. There is no overall acceleration horizontally. Therefore we can deduce that X is also 5 newtons. Similarly, I'm going to take up to be positive. Now if I take up to be positive, then any force going upwards is going to be positive and any force downwards is going to be negative. And again, the sum of the resultant forces vertically is also equal to 0, because there is no overall acceleration vertically. And we're left with 10 newtons there. Okay, so that's how we look at a situation like that with a few more forces compared to example 1. Okay, now the situation gets a bit more complicated here. Again, the object is moving at constant velocity, which means acceleration is equal to 0, which obviously means that there is no resultant force horizontally or vertically, and therefore we need to find the value of P and Q. So again, I'm going to use the same technique as in question 2. I'm going to resolve horizontally and vertically. So if I take right to be positive, then any forces in that direction will be in the right direction with positive, any force in the other direction will be negative. So what I can say is that 2p plus q, minus 40, horizontally there is no resultant force which is causing it to accelerate, therefore they're equal to 0. and therefore you're left with 2p plus q equals 40. Okay, then we're going to look at resolving vertically. Now if we resolve vertically, and I'm going to take up to be positive, what I can say is 4p minus q, that must be equal to 50. Okay, obviously it's balancing each other out. Okay, there's no overall resultant force vertically either. Now again, we need to find p and q. So we've got one equation here, another equation there. Simultaneous equations will probably be the best method here. So I'm going to make q equal to 40 minus 2p. I'm going to do 4p minus 40 minus 2p equals 50. So I've got 4p minus 2p, which is 6p minus 40 equals 50. Therefore 6p equals 90. Okay, and p equals 15. And if p is equal to 15, then q must be equal to 10. Okay, so that is how we do, again, apply Newton's first law with regards to these sort of diagram questions. Okay, now we're going to look at applying Newton's first law with regards to vectors. Now, in the previous situations we had diagrams and we could resolve horizontally and vertically. In these questions we've got vectors, and we need to just think about things in a different way. And when we look at Newton's first law, and remember what I said, Newton's first law states that an object is in equilibrium if it's, or constant velocity, if the forces acting on it balance, or if the resultant force is equal to 0. Okay, now how do we talk about resultant forces when we've got vectors? The resultant of forces in vector form can be found by adding the vectors. When you add the vectors together, especially in the ij form, what happens is that any vertical or horizontal movement will cancel each other out, or will automatically deal with each other. So adding actually has the effect of finding the resultant force. Vectors can be written obviously in ij form or column vector form. So I've got these two forces acting on object, 2i minus 3j and 5i plus 4j. Part A asks me to find the resultant force. So the resultant force, which is sum of f, comes from adding those two force vectors, 2i minus 3j plus 5i plus 4j. Okay, and when you add everything up, you get 7i plus j. Okay, 7i plus j. That is your overall resultant force. Part B asks you to find the resultant, the magnitude of this resultant force. So if I want to find the magnitude of this resultant force, like I did with vectors in Pure 1 and in vectors in the first week of mechanics, I need to apply Pythagoras on the coefficients of I and j. So 7 squared plus 1 squared, which is root 50. Okay, which becomes root 25 root 2, which becomes 5 root 2. Now I've got to be careful, we need to put the units 7i plus j newtons here, and obviously a magnitude of 5 root 2 newtons. Part C then asks to find the bearing of the resultant force. Now it would be good to draw a diagram describing the resultant force. So 7i plus j, that will be here. Okay, 7 across, 1 up. And the bearing is obviously from the y-axis, so we need to find this angle here. Now there are a variety of ways of doing it. I'm just going to draw a little diagram here, 7 and 1. I think first of all, if you can find theta, then we can deal with that pretty easily. So remember how we find the angle it makes with the x-axis, positive x-axis, tan theta equals opposite over adjacent, 1 over 7. And when you solve for tan, you get an answer which hopefully should be acute of times 180 divided by pi. So, sorry, calculator's in the wrong mode. Times by pi. Times some 180. Okay, 8.13 degrees. Okay, and then that's the angle here. But we want the bearing from the y-axis, so you've got to do 90 minus theta, which is 90 minus this angle, which is 81.7 degrees to 3SF. Okay, that is the bearing. Okay, right, so let's have a look and see what we can do in example 2. Again, we've given vectors, two forces, but they're given in column vector form. The same sort of mathematics applies. So we want to find the resultant force. So I'm going to add these two vectors together. Okay. I then find the magnitude of that vector. Which becomes 2 root 34. So newtons here, newtons there. So it's very similar to question 1. And again, the bearing of the resultant force. So remember, we've got 10 minus 6 here. So it's 10 across minus 6, so it's going to look like that. Okay, 10, 6. Again, let's find this angle. So tan theta equals opposite over adjacent. Okay, which is 30.96, etc. That's this angle here. But we want the bearing. The bearing will come from adding 90 to it. Plus 90 gives me an overall value of 121 degrees to 3SF. Okay, that's the answer for example 2. Final question, again just using Newton's first law. This time we are given 3 forces, AA minus BJ, BI plus AJ, 8I plus 2J. They all act on an object which is in equilibrium. Find the value of A and B. So remember, in equilibrium, the sum of these forces is equal to 0. So let's find the sum of these forces. Let's add them up. And let's make them equal to 0. Now, what would be a good thing here is to take out the factors of I, the coefficients of I into one bracket. So A plus B plus 8I, and then look at the coefficients of B of J. So A minus B plus 2J. Okay. Now I'll need to add to this that obviously this and this add up to equal 0, but in reality they add up to give you the 0 vector, 0I plus 0J. So if these two vectors are equal to each other, then that means the coefficients of I must equal 0 and the coefficients of J must be equal to 0. Okay, and then we're just left to do simultaneous equations. So A equals minus B minus 8. I can put that into there. So minus B minus 8 minus B plus 2. So I get minus 2B minus 8 plus 2, which is minus 6, which is 6. And B equals minus 3. And I've got my value of B. I can put that back in to there, minus 3 minus 8. So I get A equals minus 3, which is 3 minus 8, which is minus 5. So that is the value of A and B. Now, as I said, Newton's first law is quite easy enough to understand. It's well worth having got these questions here to apply them, and that is the end of the video.